we were computing Newton divided differences, and we were saying how we can actually store the divided differences in an array called dkj. And I think I had just gotten to d5(2) would be this value. And then d5(1) d5(1) is f of 4, 5, x4, x5, and then d4(1) is equal to f of x3, x4. Okay, so the summary of this is that your Newton polynomial of degree less than or equal to n. So here it is. So this is the Newton polynomial of degree less than or equal to n that passes through the point xk, yk, k equals 0 to n, where yk is equal to f of xk. Is p of x. So now you're just going to take d 0, 0. So that's the same as d of 0, 0. Okay, that's d 0, 0. And then you're going to get plus d1, 1. And that's going to multiply by x minus x naught. And now you're going to get d2, 2. And that's going to be x minus x naught times x minus x1 plus dot, 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 all the way up to dnn. And this is x minus x naught, x minus x1, all the way up to x minus xn minus 1. Okay. And here is, yep. Okay. All right. So I want to talk a little bit about the algorithms. So I want to go back to Lagrange interpolating polynomial. And I think the last thing I did was quadratic interpolation, and then advantages, disadvantages, and general interpolation. So how did I do that? Quadratic interpolation. This should have been a 4. I don't know why that's an I. Probably because my notes were confusing. It should be a 4. Okay, so I want to go to 5 and talk about the algorithm. Okay, so the algorithm for the Lagrange interpolating polynomial, if you remember, the Lagrange interpolating polynomial, let me just go back before we do the algorithm, is we have to find Pn of x, and for each one of these, we need to find Ln, these specific functions that multiply by the f values, or the y0, the y1, all the way up to the yn. And each one requires, in the numerator, you leave out the xk, and you multiply all the x minus the other x's, minus the one xk, and then the denominator is the xk minus all the other x's, okay? And so each one of those gets multiplied by the y value, and then you sum them all up, and that's the polynomial, okay? So you can actually, we figured out how to compute the Newton divided difference polynomial. The question is, how do you suppose you want to find out the value at a particular point? Okay, so say you now have, you're given set of points xk, yk, k equals 0 to n, and here your yks are some function. So you have a bunch of points and they're ordered, again, x0 less than x1 less than all the way up to xn, okay? And I want to find, so we can want to find a polynomial, so a Lagrange interpolating polynomial for the use of calculating is Pn of some value x, where x0 is less than x, is less than xn. So right now I have a bunch of data, okay? So I have this polynomial, whatever it looks like. So I have a bunch of data. Here's a point, here's a point, here's a point, here's a point, maybe here's a point, and here's a point. Okay, so I have 6 points. Well, let's just make it 5. Let me get rid of this last one. Okay, so I have those 5 points, and I can find a polynomial that goes in between them. And once I find that polynomial, I don't know what it looks like, but once I find that polynomial in between them, what I really want to know is, if I choose the value of x right here, what will it give me? What will the polynomial give me as the value for y based on the data around it? So that's what I'm trying to interpolate. Okay. So we're trying to interpolate a value for f of x when the function, actually, let me change this to Pn of x. Let's give it a different name. Let's call it x tilde. Okay. So we're trying to interpolate f of x tilde where f of x is not known. So we don't know the exact function, okay, but we do know we want to find f of some x tilde. This is now going to be x tilde. Okay. All right. So so for our algorithm, we're going to need n. Okay, so we'll need integers n. That's going to be the number of pairs. Oh, we're writing this in MATLAB, so let me adjust this a little bit from MATLAB. Okay. And we're going to need so these are our input values and input. You're going to need n, and you're going to need xi, yi, I equal 1 to n plus 1. Now, if we were actually using not MATLAB, we would use 0 to n, but because we're using MATLAB, we have to use 1 to n. Okay, so you would then set your sum. Oh, and you need to know what your x tilde is. Okay, I need to know what that is. Okay, so I would start off with my sum equal to 0. And then I would do for I equal to 1 to n plus 1. I want to set p equal to 1. And then for j equal to 1 to n plus 1 if j is not equal to I. Then I want p to equal p times x tilde minus the vector x at j times x at I minus x at j. And then we're going to end that loop. Then we're going to end this loop. And then sum is going to equal sum plus p times y at I. And then we'll end that loop. And then the value of sum is equal to my f of x tilde. Okay, so we always start the polynomial off equal to 1 because we're doing a bunch of, oh, that something's missing here. This is supposed to be, I don't believe I wrote that like that. This is supposed to be over that. This is supposed to be x at I. It's supposed to be in the denominator. And nobody said anything. Now it's right. I needed a slash between there, but that's what it's supposed to be. Okay. Any questions about the algorithm?
I don't have a question.
You don't, or you do?
I don't.
Okay. All right. So that's the algorithm for how we do it. All right. And so that was 4. That was 5. Okay. 6. let's talk about the error. Okay. So let's just say for a moment, we actually know what this polynomial is interpolating. So let's say f of x is known, and yi equal to f of xi is known for I equal 0 up to n. So now I have another set of points, xi, yi, and p of x is the Lagrange interpolating polynomial. Okay. Well, we know that f of x minus p of x is my error function. The other thing that is known is that f of x, f of xk minus p of xk is equal to 0 for all k equals 0 to n. Okay, so the Lagrange interpolating polynomial goes through each and every point. So at that point, its function value and the interpolating polynomial value is 0. So that means that e of xk has to be 0. So e of xk then, I'm sorry, e of x has to look like x minus x naught times x minus x1 all the way down to x minus xk times some function g of x. Okay, that's the only way that that thing is clearly going to be 0 at each and every xk. Okay, well, I think, is it a theorem? What do I have? A theorem in the book? I'm trying to think. There is a theorem. So there's a theorem that this g of xk is actually equal to the n plus first derivative at some c divided by n plus 1 factorial. Okay, so therefore the error turns out to be x minus x naught times x minus x1 all the way to x minus xk times f n plus 1 at c divided by n plus 1 factorial. Okay, so that's how we compute the error. Okay. All right, so there's an example in the book that I really like, and I could come up with another one, but this one's wonderful, so I'm not going to worry about it. So here's an example. All right, so the points that we have, so let's find the second Lagrange. The Lagrange interpolating polynomial. For f of x equaling 1 over x on the interval 2, 4. All right, using these points. So using x naught equal to 2. So if x naught is 2, y naught is 0.5. X1 equal to 2.75. So y naught, where did I put that thing? Oh, here it is. Is equal to 0.3636. And then x2 is equal to 4. And that's 0, y naught 0.25. I actually am going to change this problem up and use this, I don't want to use their numbers. I want to use 2.5. And then y naught would be 0.4. Okay, any questions so far? All right, so we want to use this Lagrange and find the Lagrange interpolating polynomial. Okay, so L0 is going to be x minus 2.5 times x minus 4 divided by 2 minus 2.5 divided by 2 minus 4 times 0.5 plus, excuse me, you know, guys, I'm sorry. I cannot do, I don't know why, but I have a decimal problem. I cannot think in decimals. 4/10 is 2/5. And this is 4, 1 over 4, okay. Divided by 2 minus 5 halves times 2 minus 4. And then this is times 1/2. Excuse me. Plus x minus 5 halves. No, x minus 2 times. You know what? I'm doing all the work. Why don't y'all do this? See if y'all get practice. Go ahead and get practice. Write it out. I'll finish writing it out, but I want you to write it out as well. I just won't talk while I write it out because I want you to figure this out too. I know how to do this. Okay, so now that we've completed the Lagrange interpolating polynomial, we want to find out what is the maximum error. Okay, so the maximum error, well, the maximum error we already know is going to be, this is for us, n was equal to 2. So this is going to be x minus, so the error of x is x minus 2 times x minus 5/2 times x minus 4 times the third derivative at some number c divided by n plus 1 factorial, which would be 3 factorial. Okay, so that is our error. Okay, so the question is now, how do you maximize that? All right, well, we already know that our f of x is 1 over x, or x to the minus 1. So f prime of x is equal to x to the negative minus x to the negative 2. F double prime at x is 2x to the negative 3, and f triple prime at x is negative 6x to the negative 4. Okay. All right. So we're looking for the absolute value of e of x. I want to see what the biggest this is. So that's going to be, so we want to max this. For all the x in the interval 2, 4 of x minus 2 times x minus 5/2 times x minus 4. And then we need the third derivative at, and the biggest the third derivative could be. So the biggest f prime can be on that interval is when x is equal to 2. Okay, so when x is equal to 2, we get 2 to the 16th. We get 1 over the 16. So this is an absolute value, 6 over 16. Okay, and the 6's are going to cancel. So therefore, we just have, actually, it doesn't even really matter. This becomes 6 over 16 here. So that's the biggest that can be. All right, so now what we need to do is find the maximum of this function. Oh, I don't want to call it g because I called something else g, which is just x minus 2 times x minus 5/2 times x minus 4. Okay, so now what we need to do is take the derivative of that and set that equal to 0. All right, so we're going to get f of x. So our function, oops. What did I say? It was x minus 2 times x minus 5/2 times x minus 4. So that is x cubed minus 17/2 minus 17/2 x squared plus 23x minus 20. So this turns out to be x cubed minus 17/2 x squared plus 23x minus 20. All right, so its derivative is easy to find because we maximize this. So f prime of x. Oh, I don't want to call it f of, I need to give it a name. Let's call it e naught of x. Okay, so e naught prime three x squared minus 17x plus 23. And we need to set that thing equal to 0. Okay. (17x minus 20, right? Okay, so x turns out to be 1 and minus 23rds. I think I wrote the wrong number. It's minus 20, it's plus 23, isn't it? 3x squared minus 17x plus 23. Oh, these are not cute. Okay, much better. So I get negative 2.23 and negative 3.43. And neither one of those is in the interval. Do you see that? Neither one of those is in the interval. X cubed, 3x squared minus 17x plus 23. Let me make sure I did that right. 3x squared by plus, is it plus? Oh, it's minus 17. Target, I still got it wrong. Okay, 3x squared minus 17x plus 23 equals 0. Okay, now I get the positive roots. So now I get 3.43 and 2.23. Okay, now one of them is, now they're both in the integral, actually. Three point four three, 2.23. Great. Second derivative test. Let's make life easy. E naught double prime of x. 6x minus 17. Okay, so E naught double prime at 3.43 is positive. So that's a local min. And E naught double prime at 2.23 is going to be negative. So that is a local max. All right. We already know at the endpoints, our function is 0. So we don't need to check the endpoints. So therefore, the maximum occurs at 2.23. Okay. So therefore, our error, absolute our error, is less than or equal to our 1/16. That comes from back here. I'm sorry, and I forgot the 6 factorial. 1/3 factorial, so that's the 1/6. So we get 1/16 times the biggest x minus 2 times x minus 5/2 times x minus 4 can be, and that's less than or equal to 1/16. And the biggest this thing can be is what the derivative is at the critical point. So that means we need to put in the critical point for the function. So when I put the function, okay, I'm confused. Oh, I got to go to the original function. The original, yes. When I put what the function actually is, so f, so that big part E naught, I get 0.10.1099. Okay. And that's actually not too bad. 0.1099 divided by 16. Point 006 8687. And I feel like I made a typo in here. I'm trying to see if I did everything right. That derivative is less than 0. So that is definitely a local max. So I take the max, put it back into, took the derivative, set it equal to 0, use the second derivative test to get that that's a local max. Then went over to here, put it back into what I called E naught. Oh, E naught. Yes, put it back into E naught. I did. Okay, That looks good. All right.
Excuse
I
me,
think I need to double check my math, but I think I'm good. Yes, ma'am.
the error part, the last line, I don't understand how you get there.
Okay, so hold on a minute. I'm trying to bring up, I can't, that's why I can't see you. Okay, so what did you say? The last line?
Yes, the error. Starting from
Okay,
the
so the error should be less. Here's the error. So it's the maximum of this function.
okay.
The error is the max of this function,
Oh,
where this piece is this. So that's the biggest that the third derivative can be on the interval 0, on the interval 2, 4. So the biggest it can be on the interval 2, 4 is 6/16, and then it's still divided by 3 factorial.
all right.
So then I get 1/16. So therefore I'm trying to maximize that. So that's what E of X is.
Okay.
Okay. And so then I said, let me for a moment get rid of the 1/16 and just maximize the rest of it. And then in the end, multiply by the 1/16 when I'm done.
Oh, okay.
Okay. So then I went and I took that function and I took its derivative. I set it equal to 0. And these are my critical points.
Okay.
And I used the very wonderful second derivative test. To show that this is the local max is here. So now that I had a local max, I know that the error is less than 1/16 times the max of that function. But the max of that function is just to take and put in the 2.23 into this function. And when I put in 2.23, unless I did it wrong, let me just double check. I put 2.23 into the function. Yes. When I put 2.23 in there, I get 0.1099, actually 17, if you want to be specific. But it's, I chopped off some of the
Okay.
values. If you want the exact up to 8 decimal places. You get 0.109927 and some other stuff.
Okay. That's okay.
Okay. All right. So what we will finish up with on Thursday is we are going to do, I will give you the algorithm for the Newton divided difference, and then we will go into cubic splines. And then when we're finished that, we'll be finished our polynomial interpolation. Okay.
Okay, thank you.
All right. Any questions? Okay.